All right, future captains, welcome. I'm your instructor, and today we're going to tackle a subject that's not just on your CPL exam, but it's going to be your co-pilot on every single flight: meteorology. We're starting with the absolute basics, the very air your aircraft flies through. Getting this down is your first big step to acing those exams and becoming a truly sharp aviator. But before we get into all the numbers and layers, let's just take a step back and think about something fundamental. What is the one single environment that controls the performance, the safety, and the efficiency of every flight you will ever take?
And the answer, of course, is the atmosphere. It's so much more than just empty sky. For us, it's a huge, complex, and dynamic ocean of air. Think of it that way. We're not just flying, we're sailing through this invisible ocean. And your ability to read its currents and its conditions is what will make you a great pilot.
So, here's our flight plan for this explainer. First, we're going to define our ocean of air. Then we'll look at what it's made of. After that, we'll do a virtual climb through its different layers, and we'll finish up with the most important benchmark for any pilot, the International Standard Atmosphere, or ISA.
Okay, first up, let's get a really clear idea of what we're working with. It's so easy to think of the air as nothing, just empty space. But it's not. It's a real, physical substance, and it's the entire reason flight is even possible.
So here's the key definition you need to remember. The atmosphere is a mix of gases, and it's held tight to our planet by gravity. Without gravity, all this air would just float off into space. This envelope gives us air to breathe, it protects us from nasty UV radiation, and, most importantly for us, it's the medium that our wings bite into to create lift. No atmosphere, no flight. Simple as that.
All right, we know what it is, but what's it actually made of? This is where you need to start paying close attention, because the specific numbers here are prime material for exam questions. Examiners absolutely love to test this stuff.
Now, when you look at this chart, one thing should just jump out at you. The whole show is dominated by just two gases. We pilots talk about oxygen all the time, right? But look, nitrogen makes up a massive 78% of the air. Oxygen comes in second at 21%. Everything else, argon, CO2, all the others, they're all squeezed into less than 1%.
Just remember this number, 99%. It's that simple. For your exams, if you can just lock in that nitrogen and oxygen together make up pretty much everything, you're on the right track. It's a simple but absolutely critical fact.
And here's a detail you'll want to put a big star next to in your notes. This pops up on CPL exams all the time. They love to ask about the ratio of nitrogen to oxygen. By volume, it's about 4 parts nitrogen to 1 part oxygen. But by weight, that ratio changes to 3 to 1. You've got to know the difference between those two.
Okay, so we know what the atmosphere is made of. Now let's imagine we're in a rocket, climbing straight up from the ground. We're going to explore the vertical layers of the atmosphere, because each one has totally different characteristics that directly affect us as pilots.
Our first layer, the one where we spend most of our lives as aviators, is the troposphere. And a good way to remember it is this: if it's weather, it's happening here.
This is our world, right? Almost all, 99% of the planet's water vapor is trapped right here in the troposphere. And water vapor means weather. Clouds, rain, thunderstorms, turbulence, you name it, it's happening in this layer. Also, notice its height isn't uniform, and the temperature consistently drops the higher you go.
This slide shows a really key concept you need to grasp. It's simple. Warm air expands. So, at the hot equator, the air expands and pushes the top of the troposphere, the tropopause, way higher. At the poles, the air is cold and dense, so it's much lower. This is a classic CPL question, so be ready for it.
So, as we climb up and push through that boundary called the tropopause, we enter a whole new world, the stratosphere. And it's a completely different environment, much more stable.
The key word for the stratosphere is stability. There's basically no weather here. And check out the temperature. It actually gets warmer as you climb higher. So why is that? It's because of the ozone layer. It's sitting in here, soaking up ultraviolet radiation from the sun, and that process heats this layer up. This temperature inversion is what makes the stratosphere so incredibly smooth and stable.
Okay, let's keep climbing. We're now passing through the final 2 major layers that are relevant to atmospheric science. We won't be flying our Cessnas or Airbuses up here, but you still need to know the complete structure for your exams.
So here's a great summary of our climb. The most important thing to burn into your memory here is the temperature profile. Just look at the pattern. Temperature decreases in the troposphere, increases in the stratosphere, decreases again in the mesosphere, and finally increases in the thermosphere. Down, up, down, up. If you can remember that pattern, you've got the layers down cold.
Now listen up. We're moving on to what is probably the most important section of this entire lesson, both for your exams and your whole career. All of our instruments, our performance charts, everything is calibrated to a standard model of the atmosphere called ISA. You absolutely, positively must know these values by heart.
So think of ISA like this. The real atmosphere is messy, and it's changing all the time. To make any sense of it, we need a fixed, universal ruler that everyone in aviation agrees on. That's ISA. It is our baseline, our reference point for calculating performance and measuring altitude.
You need to memorize these three values. No way around it. At mean sea level, ISA assumes a temperature of plus 15 degrees Celsius, a pressure of 1,013.25 hectopascals, and a density of 1225 grams per cubic meter. These are the absolute cornerstones of altimetry.
This slide is definitely one you'll want to screenshot. ISA also defines exactly how temperature is supposed to change as you climb. The standard lapse rate is a decrease of 1.98 degrees Celsius for every 1,000 feet you go up, right until you hit the tropopause at about 36,000 feet. At that point, the temperature just stays constant at a chilly minus 56.5 degrees. These numbers are pure gold for your exams.
So here's the punchline. This is why ISA is so important for us in the cockpit. We are constantly comparing the real atmosphere outside to this standard model. The difference between the actual temperature and what ISA says it should be at your altitude, that's called the ISA deviation. And that one little number tells you a huge amount about how your aircraft is going to perform.
Okay, so let's do a quick final check. We've covered the ingredients of the air we fly in, mainly nitrogen and oxygen. We've climbed through the layers, the troposphere where all the weather is, and the stable stratosphere with its ozone. And we've drilled down on ISA, the benchmark for all of our operations. These really are the foundational building blocks of aviation meteorology.
So, I'll leave you with this question to think about. Knowing the standard is one thing, but how does a hot day where you might have an ISA deviation of plus 20 actually affect your takeoff roll? This exact question leads us right into our next essential topics: pressure, temperature, and density. Good luck with your studies, and we'll see you in the next one.